Okay, let's talk about RC circuits. Recording. I already did this lecture, but I realized I forgot to turn on the recording button, so take two. So what we're dealing with, these are non-steady state circuits. In other words, the current is changing. As a result, you're going to see in a lot of the graphs and things lowercase I. Lowercase I usually means a changing current. Capital I usually means a constant current. It's not hard and fast that way, but that's often what it means. So the idea here is we've got a battery, a resistor, and a capacitor in the same circuit. When we first close the switch, the capacitor acts like a wire. Okay, you can ignore the capacitor when you first close the switch. That means the current through here is just going to be the voltage on the battery divided by the resistor. But over time, charge is going to collect, and then after a long time, there's no current flowing. So a capacitor, after a long time, acts like an open switch. Remember that. That's the key to this whole thing. Initially, capacitor acts like a wire. At the end, after a long time, then the capacitor acts like an open switch. Okay, that's the whole idea. And so, if this is the charge on the capacitor, and this is Q max, right? The maximum charge that can be on the capacitor, given by the capacitance times the voltage, the potential of the battery, right? The EMF. This goes up like this. Initially, 0 when you first close the switch, and the capacitor is charging up. And then that's what happens. As a result, also, the potential difference across the capacitor goes up and approaches as an asymptote, not that kind of volt, V, the voltage on the battery, or the EMF. You'll see it that way sometimes as well. The current, the initial current, I naught, given by the EMF of the battery divided by the resistor, goes like this. And it approaches 0 asymptotically, right? And the potential difference across the resistor, given by the EMF of the battery, also gets to be less and less as time goes on. So this is what the graphs look like. This should look familiar. This looks like e to the negative t, some time constant kind of thing, right? Like drag. So now looking at this circuit, if this is uncharged and the current or this switch is switched to A, then this is going to charge up, right? So initially, the current is going this way. It goes around, and you get positive charge collecting here, negative charge collecting here, right? Also on the resistor, this is going to be the positive side, right, and the negative side, so the potential drops as you go across this resistor when the current is flowing that way. But when you have it closed today for a long time, then this gets charged up, right? And so as this is charging, by the way, we need to keep in mind Kirchhoff's loop rule. And the loop rule tells us that, so the EMF on the battery is going to be equal to the voltage on the resistor, which is going to be I times R, right? Plus the voltage on the battery, or on the capacitor, which is going to be Q over C. Notice lowercase q because Q's potentially changing. I is Q over T, so R times Q over T plus Q over C, or dq dt here. Right. And so then over time, this gets to be 0, and then all the potential difference is across the capacitor. That'll be Q over C. Okay, then though, once this is all charged up, if we turn the switch now to B instead, what we have here is the capacitor acting like a battery. All the positive charge here wants to go away, the negative charge wants to go away, and so now I end up with current going this way. Right. And now in this case, the potential difference across this has to be equal to the potential difference across here. So notice now I've got positive and negative. The potential difference on the resistor switches direction. And so now going across it this way, R times dq dt, R times the current, is equal to Q over C, the charge on the capacitor divided by the capacitance. Right? So this is the voltage on the resistor is equal to the potential difference on the capacitor as it's discharging. Right? And so the discharging works the same way with those types of graphs. Right? So as it's charging, now we can see what those equations are. And so let's fill in QT, Q is a function of time, is given by CE. So this is the charge on the capacitor. CE, C times the EMF on the battery, represents the maximum charge. And so then, and this is approaching that asymptote, right? So this is going to be 1 minus e to the negative t over tau c. Tau is the time constant, right? And so that's what that is. And it's in the next slide. Tau is equal to R times C. That's just the resistance of the resistor times the capacitance of the capacitor. That's it. I is a function of time. The current is a function of time. The initial maximum current is just going to be the EMF divided by the resistor. Right? EMF divided by the resistance. And then this one is decreasing. So that's times e to the negative t over tau. The format for all of these equations is really the same. If it's increasing and reaching an asymptote, what you do is you put here in front what that asymptote is. Q max, V max, the EMF of the battery, something like that, times 1 minus e to the negative t over tau. If it's something that's decreasing, then this coefficient in front is just, the starting point. In this case, that maximum current given by the EMF of the battery divided by the resistor times e to the negative t over tau. They're all the exact same form. Just some coefficient given by the maximum, either the starting point or the asymptote, times either this or this, depending on whether it's going up or down. Right? They're all that same way. And so then the voltage on the capacitor as a function of time is going to be given by the EMF. That's the maximum voltage that the capacitor will have after a period of time, the EMF of the battery. And it's approaching that asymptotically, so it's 1 minus e to the negative t over tau. Okay, that's it. And so this should look familiar from this form of the equation from drag. Right, and so we've got, if this is Q max right here, the idea is that after one time constant, so here tau, which is equal to RC, then it reaches 0.63 of Q max. So in one time constant, if something is going up, it reaches 63% of that maximum value in one time constant. For the voltage on the capacitor, this is the EMF, so that's what it's approaching. Then, after one time constant, also it's at 63% of that maximum value after one time constant. Right. But if it's something that's decreasing, something like the current, right, given initially by the EMF over the resistor, and it's decreasing, then after one time constant, it's at 0.37 of that maximum value. It's at 37% after one time constant. And the same thing is true for the voltage on the resistor. Right. It starts off with the EMF of the battery, but then after one time constant, it's at 37% of the EMF. Okay. Discharging is similar. Right. So here's charging, except now we just switch. So now the current is decreasing if it's discharging. So if the current is decreasing, now it's Q is a function of time. It's going to be capacitance times the EMF times e to the negative t over tau. All right, the current also will be decreasing, so this is I as a function of time. Right? Imagine it'll be high current at first, but then as it continues to discharge, it all just goes away. So this is the initial and the EMF. So C, this is given by Q naught. Right, so we could say this Q naught, e to the negative t over tau. Here it's the lowercase q. The voltage, again, is given by Q naught over C, and that's over R, right? V over R would give you the current, e to the negative t over tau. And then the last thing we're looking at is the voltage on the capacitor as a function of time, and that would be Q naught over C. This also is decreasing, e to the negative t over tau. This might not be in the packet, but it should be there. Okay. Well, this might not be there because in the packet it's this. Q is a function of time, so it's this function divided by C. Right. All right, so let's take a look at some examples.